Energy isn't something we usually associate with organic materials. When people think about energy, they think about electricity, fuel, or batteries. Not plants. Not leaves. Not organic waste. But here's the part most people don't realize. Organic materials are actually one of the oldest and most fundamental ways energy is stored. And understanding how that works changes the way you see modern energy systems. At a surface level, it seems simple. Plants grow. They dry out. They can be burned or decomposed. And somehow, that produces energy. But that explanation skips over something important. Because organic materials don't just contain energy randomly. They store it through a very specific process. And that process starts long before the material is ever used. It starts with sunlight. Plants absorb sunlight through photosynthesis. But instead of turning that energy into electricity, they convert it into chemical energy. That energy is stored inside the structure of the plant itself. In fibers, in sugars, in complex organic compounds. So when you look at a piece of wood or plant material, you're not just looking at matter. You're looking at stored energy from sunlight. Energy that has been captured, converted, and preserved over time. But this is where things start to get more complex. Because storing energy is one thing. Accessing it is another. Unlike electricity, which can be used instantly, energy in organic materials has to be released through a process. Burning, decomposition, gasification. Each of these methods breaks down the material to release the stored energy. And that introduces a delay, a transformation step. So instead of on-demand energy, you have process-based energy. And that difference matters more than it seems. Because now, the system depends on conditions. Temperature, oxygen levels, moisture, material consistency. If those conditions aren't right, the energy doesn't release efficiently. So even though the energy is stored, it's not immediately accessible. This is where many people get confused. They assume that having the material means having the energy. But that's only partially true. The real issue isn't whether energy exists in the material. It's whether the system can reliably convert it. And that's the hidden layer most people don't see. Because on the surface, organic energy feels simple. You have biomass. You use it. You get energy. But underneath, it behaves more like a controlled environment than a simple fuel. Think of it like cooking. Having ingredients doesn't guarantee a meal. You still need the right process, timing, and conditions. And if something is off, the result changes. Organic energy systems work in a similar way. They require balance, consistency, control over variables that aren't always obvious. And that's why they're often misunderstood. Not because they're complicated in theory, but because their behavior depends on factors people don't usually consider. Once you start to see that, something shifts. You stop thinking of organic materials as just fuel, and start seeing them as part of a system that captures energy slowly, stores it over time, and releases it through transformation. That perspective also explains why these systems are being revisited today, not as replacements for modern energy, but as complementary systems, ways to diversify how energy is stored and accessed. Because unlike solar, which depends on real-time conditions, organic materials store energy over time. They act more like a natural battery, but again, with a different type of limitation. Not storage capacity alone, but conversion control. And that brings us to a key turning point. The real issue isn't whether organic materials can store energy. It's understanding how that stored energy behaves when you try to use it. Because once you understand that, you stop expecting instant results, and start thinking in terms of systems, processes, and timing. And that's where real clarity begins. If you want to explore how these organic energy systems are being used in practical setups today, there's a structured breakdown in the description. You can also find a step-by-step framework that explains how these systems work in real-world conditions. And as always, the goal isn't to simplify the idea. It's to understand it deeply enough that it actually makes sense when applied.